Hello and welcome. So today we're going to take a step away from our linear kinematics and start looking at things in an angular scale. Okay, before we do that, there's a couple of things we need to go over. So we need to talk about radians. What are they? So radians are defined as the length of an arc divided by the radius of an arc when we're dealing with things going in circular or angular motion. Okay, so our radian is represented as theta, and if you were to look at the circle I've got over here in the corner, you can see that the length of the arc would be the displacement round the arc S, and that the radius would be R. So we get the theta is equal to S over R. Okay. Now, for one full circle, that'd be one full 360 degree turn. And to convert that angle into radians, you would have the circumference of the circle, which would be 2 pi r, divided by r, which is the radius of the circle. The two r's cancel, and so we can show that 360 degrees is 2 pi radians. Okay. Now what we're going to do in the next page is we're going to do a couple of conversions just to get used to converting between radians and degrees. So I've got 4 angles we're going to work our way through. So first of all, we've got 100 degrees, and we're going to times that to convert it from degrees to radians. We're going to times it by pi divided by 180. Okay, and what that does is it gives us the radian value. So for that one, it's 1.7. I'm going to use a different color other than black so we can. Okay. I'm going to go through these with you at the same time, so if you're wanting to do these ahead of me, that's fine. Round this one to 1.4. Okay, and again, all we're doing with all of these is timesing them by pi divided by 180. 198 times pi divided by 180 is 3.5. Okay. And moving on to our next side, I've noticed a couple of mistakes I've made writing this up, so there should be a pi there and a pi there. Okay, so now to convert from radians to degrees, you take whatever number you have in radians and multiply it by 180 divided by pi. Okay, so if we put that in a calculator, 180 divided by pi times 4 pi, that's going to come out as 700. I'm going to use a different color as well. Let's make it look neat. 720 degrees. Okay, and 0.45 pi is going to come out as 81 degrees. 3.5 pi, 630 degrees. And 20 pi, oh, I'd like 20 pi's. Not the all at once, but just in general. So, that would be how we'd convert from degrees to radians and radians into degrees. Okay. Moving on, what we're going to look at are our angular motion versus our linear motion. Okay, now up till this point we've been dealing with displacement, velocity and acceleration, and we know that displacement's S, initial velocity is U, final velocity is V, and acceleration is A. Okay, and what we have here now is we have our angular versions of these that we're going to look at. So we have our angular displacement, which has the symbol theta, okay, and is measured in radians. We have an initial angular velocity, right? If our initial velocity is meters per second, our initial angular velocity is going to be measured in radians per second. Okay, and it has a symbol omega naught. Okay, now yes, omega looks like a curvy W, but it's a Greek letter, the small omega, and then this is a subscript 0. Okay, our final angular velocity is just omega. Okay, and it's also measured in radians per second. And the clever among you will have guessed that angular acceleration is going to be measured in radians per second per second. Okay, so r rads to the minus 2. Okay, and our symbol for angular acceleration is alpha. So another Greek letter there. Kind of looks a bit like a fish, but it's an A for alpha. An alpha. Okay, and so these are our symbols. Now, these two are very similar in what we're going to do. So we're going to first look at discovering what these equations of angular motion are. Okay, now, as you can see from our unit, the initial angular velocity is radians per second, which means that angular velocity must also be the rate of change of angular displacement. So, our angular velocity, omega, must be equal to d theta by dt. And using the same principle, alpha, our angular acceleration, would be equal to d omega by dt, which is also equal to d squared theta by dt squared. Okay, now what this leads us to, if you were to do the derivations, is equations that you're going to be very familiar with in a way. Omega is equal to omega naught plus alpha t. Theta is equal to omega naught t plus a half alpha t squared. And omega squared is equal to omega naught squared plus 2 alpha theta. And so if you compare these with their linear counterparts, you've got v is equal to u plus at, s is equal to ut plus a half at squared, and v squared is equal to u squared plus 2as. Okay, so the equations are very similar in a setup like that. And the one I've not shown you yet, if we were to have velocity is equal to displacement over time, if we were to write that in the angular form, omega would be equal to theta over t. Okay. Now these are going to be really useful for working out things that are moving in a circular angular motion. And the next few videos that I'm going to be doing are focusing on solving problems using these equations. Okay, so hopefully this has been a good introduction to the angular motion equations, and a sort of brief where they've come from. Okay, I hope you